Probably wait 5 minutes before getting started.
Yep.
Is my screen showing up okay?
Yep. I started recording, by the way.
Well, everyone, we're gonna wait a couple of minutes before starting, but I put the link to the Google Cloud in the chat, and you can open that up and run the code and follow along with my presentation. But yeah, we'll wait a couple more minutes. Okay, so I think I'll get started. Um, this is recorded anyway, so if anybody's missing it, they can tune in afterwards, or you can rewatch anything. I do have time for questions in this presentation, so please do interrupt me if you have any questions. And worst case, we just won't get through all the code. I think it's better to address questions than to go through just me talking about code the whole time. Um, so yeah, just feel free to interrupt at any time. You can unmute yourself. You can raise your hand in chat. I'll try to follow along. So I'll put the link in chat one more time if anybody's just arriving. You can open this up. It should open up a page that looks like what I have here on my screen. And then you can run the code and follow along. So I'm in this presentation. Uh, I'm using R, and I'm using the packages that are available in Google Colab, which is the base R functionality and then the tidyverse package. There's a lot of extra stuff in R that can do a lot of things much more efficiently than I'm showing you here in this presentation and with increased functionality, but it takes a really long time to install packages in Google Colab. So I'm just using the base R for the most part. There is one package we're going to use that's external to Google Cloud, and it's Frank Harrell's package, who I talked a lot about yesterday, because he has some really good functionality for validation that I want to show you guys. Um, so just run this box in your browser, and it'll take a couple of minutes, and then while I'm giving the introduction, it'll install that package for us. Takes about 3 minutes for my testing. So we're going to be using R. And it won't be scary if you're not familiar with R. It's quite easy to follow along the code, and I'll explain everything that's going on. Doing regression modeling in R is based around this idea of the R formula, and the form of this is you have some response variable tilde terms, and this reads as a function of. So the response is a function of the terms, and this is really the core of the code for all regression modeling in R. And to everybody that's joined since I started talking, I'm going to put the. I'm not sure if they can scroll back up and read the chat, but I'll put it again anyway. You can open this link and follow along the code and just run this first box. So it took 30 seconds for me. Um, so the terms on the right here are the additive components of general linear model. So if we're modeling blood pressure as our response variable, we will say blood pressure is a function of sex and age. And that's how it works. And what this translates to from what I showed you yesterday is that your outcome variable is a function of it adds an intercept automatically if you're using a regression model that has an intercept, and then it adds the slope terms for your terms that you added automatically. So that's how it reads it. And then you just package this formula in whatever model you want to use. So if you're doing linear regression, you use the LM function, and I'll show you all this in a second. If you're doing logistic regression, you use the GLM function, and you tell it to use a binomial link. And the way this code will look, and again, we'll go through all this, but you make a linear model using the linear model formula with your formula in here, the linear model function with your formula, logistic model with the GLM function with your formula. So it's quite simple to make models very quick. Um, Another thing I'll say is that this left arrow here is the same thing as an equal sign in R. They're just used interchangeably. You can use either one you want. Um, so we're going to be using, as I said, base R, but also the tidyverse family of packages, especially Dipler and ggplot2. ggplot2 is the package that lets you create really nice publication quality images very easily. And Dipler is a really easy way to do data manipulation. So one thing that'll be a bit unusual for these, if you're not familiar with R, is this symbol. This basically means carry an object forward, and what this lets you do is chain a bunch of operations together without explicitly saving the intermediate objects. So if you have some data and you want to do something to it, then you can do that something and then call this, put the symbol again, and then do something else, and it just carries this object forward into all the functions. And the equivalent, if you just wanted to do this manually, which you could, would be to save some intermediate object using the base object and then call another function on the intermediate object, which can get messy quickly if you're doing a whole bunch of operations. And you'll see what I'm talking about in a second. And to everybody that's just joined in the last few minutes, the link should be in the chat for this code. And please just run this first box to install a package, and then you can follow along with what I'm doing. So today we're going to be working with heart failure prediction data set from Kaggle. This is a real life data set. They combined five heart failure prediction data sets from three from the States, one from Hungary, one from Switzerland that had common variables. So this data set has 11 possible predictors and then an outcome variable that's heart disease. And they have 918 individuals. So it's quite a cool data set. Um, so these are the variables that are in this data set as described on Kaggle's website. We have age, we have sex, we have whether they're having chest pain, so what the type of chest pain they're having, or if they're asymptomatic, their blood pressure. It's systolic blood pressure from the numbers, it seems, although it's not explicitly described. Their cholesterol level, and I think this is a typo because this isn't an actual unit, but we'll get into that. Um, Whether they have high fasting blood sugar, so whether they have unhealthy blood sugar or not, their EKG values at rest, ECG in the States, their maximum heart rate in an exercise test, whether they had pain in an exercise test, and then some other parameters having to do with their EKG in this exercise test, and then whether they have heart disease. So this is the data set. Today, we're not going to look at everything to keep things simple. We're just going to focus on six variables that are, easy to understand what they're doing, and it will help us with our interpretations. So I've chosen one continuous variable that we're going to treat as an outcome, even though it's sort of a predictor, which is resting blood pressure. One variable which we're going to treat as an outcome, which is the actual outcome variable in this data set, which is heart disease. Two continuous variables that we're going to treat as predictors, which are age and cholesterol, and then two categorical variables that we're going to treat as predictors, which is sex and fasting blood sugar. So this will be a sort of toy example, but it'll let us explore all the relevant stuff for continuous predictors, categorical predictors, continuous outcome for linear regression, and then a binary outcome for logistic regression. So that's what we'll do. We're going to follow this basic analysis framework, and this isn't necessarily best practice, but it's a good way to show all the aspects of what I was talking about yesterday in a sort of systematic way. So we're going to start by looking at some descriptive statistics, just poke through the data, see what it looks like, see if there's anything we need to clean. And then we'll look through the relationships between the predictors, and that'll help us look at if there's any collinearity, which I talked about yesterday, which could make it very hard to make predictions. We'll do univariate regression for each variable of interest. So the relationship in a univariate way between blood pressure and each of these predictors, or heart disease and each of these predictors. And this isn't really something I would actually recommend doing in your real work. Uh, but for this example, it'll let us one at a time see what are the effects of these variables. And my focus today is really going to be on making these models and then interpreting the outputs. So this will let us do that and really understand what the model is telling us about what's going on. And then we'll combine them all in a multivariate model. Um, so as I said yesterday, what I would recommend doing is pre-specifying this model without doing any of these previous steps, like based on your a priori knowledge about your research question, what variables are going to matter, and then pre-specifying that that's where you're going to put in your model. That's best practice. But I'm also going to show you how to do model selection. So how to do forward and backwards variable selection to see what the best fitting model is. But as I said yesterday, be very careful when you're doing this sort of thing, but I just wanted to show you how to do it. And then we'll look at some alternate model specifications. So I'll show you especially how to add interaction terms and look at possible effect modification in these models, as well as how to do some polynomial stuff if you want to get more complicated with your variables. I'll show you how to check assumptions. And throughout, we'll really be, as I said, focusing on interpretation. So how you might make conclusions or predictions about future people or that kind of thing. So we're going to start by loading the data set. I've downloaded this data set from Kaggle and I uploaded it to GitHub so we can just read the CSV. So this is just pulling basically the Excel file from GitHub and putting it in an object in R. We're also going to load the tidyverse library, as I said, which is automatically included in Google Colab and which is super powerful, and we'll get into that. So let's just start looking at some summary statistics about the data set. So this head function in R just shows you the top of the data, and the structure function shows you a summary of the data and what data types you have. So we'll just run that. So as expected, we have 12 variables And R just automatically figured out that these headers here were the names of the variables, so that's convenient for us. And then it tells you what type of variable they are. This is the first six rows of the data frame. And then similarly down here, these two functions do similar things. There's just ways to get an overall summary of your data. Um, it tells us that we have 918 people, which is exactly what we thought we were going to see, 12 variables. We have, as we expected, age, which is an integer value, sex, which is a character value. We actually want this to be a categorical variable, not a character. So a character meaning like a string of characters. Um, but it's M's and F's, obviously. So we're gonna have to tell R that this is a category. These are categories. These aren't just words. So we'll get into that. We're not going to be using a few of these, but they're all here, and there's descriptions on them. The ones we're going to be using are fasting blood sugar, which is integers, but again, we want to make that categories. Um, Cholesterol, which is continuous integers, so that's good, and blood pressure, as well as heart disease, are outcome variable. So everything makes sense just from this basic loading and exploration of what's going on. So we'll move on. So what we're going to do is simplify down this data frame because we don't want all these variables. We're just going to look at a subset of them. So the first thing we're going to do, and this is using the Doppler library, we're going to select the six variables we care about. So quite human readable. We're going to override the object of the data frame by selecting just those six variables we care about. And then we're also going to tell R that the sex variable is categorical, and this as factor function is what tells R that this is a category, and that the blood sugar variable is also a categorical predictor. So we're just telling R that select these six variables we care about, let's replace these two with categories instead of what they currently are, which is a character and an integer. And then we'll rerun the summary function and make sure that everything worked correctly. So we now have our six variables. Our ages range from 28 to 77, which makes sense with a mean around 54. Our data set's mostly males, which we're going to have to keep in mind. Our cholesterol values range from 0 to 600. And obviously, 0 here is already a red flag because nobody can have a cholesterol value of 0. So there's something going on here that we're going to have to dig into. So doing this kind of work to make sure that your data set makes sense is essential. And here there's something not making sense. So we'll have to dig into that. 214 of the people have a high fasting blood sugar. Our blood pressures range from 0 to 200. And again, 0 blood pressure is not possible. So this data set has something going on where there's people with zeros here that clearly don't actually have the value 0. So we'll have to dig into that. Um, we're also going to make a table of our outcome variable, heart disease. And we see that 508 of the people had the outcome and 410 didn't. And we can already start thinking about sample size. So with 508 people, if you apply that 20 events per parameter rule of thumb that I was talking about yesterday, then that's 25.4 degrees of freedom we can accommodate in our predictor parameters. So we only have six variables. So that's way more degrees of freedom than we need, which is perfect. So we can use all our variables and we can even get fancy and add some complicated stuff, interaction terms, polynomials, and we don't have to worry that we don't have enough data to make reliable predictions or get stable effect estimates. So that's encouraging. This is just going through the values. So let's take a closer look at the continuous variables because for sex and fasting blood sugar, you can just see explicitly what's going on, but it can be sort of hard to tell what's going on with these 5-number summaries of these continuous variables. So we'll plot some histograms. This line is asking, are there any missing values in this variable? And then we'll plot histograms of age, cholesterol, and blood pressure. And we'll ask if there's any missing variables in all three. And we'll also plot our resting blood pressure. So first off, there's no missing values in these variables, which is good to see. Our ages are looking like a nice normal distribution between, 28 and 80, which is perfect. Cholesterol, though, we have a problem here. There's a whole bunch of people, like 170 of them, that have a cholesterol value of zero. And this doesn't isn't said anywhere on the Kaggle website or anything, but my impression is that these values are just missing. And they've chosen zero as their missing value number, which is a little ridiculous because you might not realize that if you're doing this blindly. But we're going to have to tell R that these are not zeros, that they're missing because nobody can have a cholesterol value of zero. So we'll do that in a second. Um, these are our blood pressure values, and you can see that there's something weird going on here. Um, and what's weird is that there's these spikes every 10 millimeters of mercury, and sort of every 5 as well. So this is just a sort of real life thing that when a physician is taking blood pressure, if they're doing it manually, which must be what's going on here, they'll just write down some number that's rounded to the nearest 5 or 10. And you can see it in the plot here as well. So this is definitely suboptimal for our purposes, but it's the reality of the data. So we know that sort of all these values are rounded from the values around them. And it's a bit, we don't really have time to go into this today, but what we could do if we wanted to deal with this is say for these people, that's spread them out over a normal distribution around the peak, and then we could get a more normal looking blood pressure curve, and that would probably be closer to the truth than what this is. But we'll just leave it as is for now, and we'll see how it affects our assumptions later on. And it does mess things up a little bit because of these errors in the measurement of blood pressure. Um, right. So those zeros in cholesterol, and there's actually one person in blood pressure that has a zero. It's just one person, but there's a lot of them for cholesterol. We need to replace those with missing values so that R knows that these are not zeros. And when it's trying to fit the regression models, it's not trying to fit these zeros. We need to tell it that these values don't exist. So we're going to do that. Again, we're going to use Dipler to do that. The mutate function just creates new variables or overrides existing variables. So we're going to tell it that if cholesterol is zero, we're going to replace cholesterol with Na, which is missing. And if it's not zero, we're going to keep the value. So this if else function is very powerful in R. So it's just saying if this is the case, do this, otherwise do this. So we're going to replace cholesterol with missing this if it's zero, same for blood pressure. And then we're going to replot and make sure everything worked nicely. So now R knows that there's 172 missing values for cholesterol. So that's good. And we get this more normal looking curve of the cholesterol values that remain. And then same for blood pressure. We've eliminated that zero value and we get a more normal looking distribution. So that's good. Um, and then one last thing before we move on to regression itself is we want to make sure that there's no collinearity between these variables. And, I can tell you before running this code that there isn't going to be any collinearity because these variables, which is age, sex, cholesterol, and blood sugar, obviously are not going to be perfectly correlated with each other because these are, well-defined variables that mean very different things. And it's not plausible a priori that there will be high collinearity. But you need to do this kind of check, especially if you have more complicated variables that might be, functions of each other, to make sure that your regression models will work and that you won't have weird problems. But in this case, uh, the males in our data set tend to be slightly older, but it's no big deal. There isn't much of a pattern between cholesterol and age that's visually obvious anyway. The people with high fasting blood sugar do tend to be quite a bit older. So, this isn't collinearity, but there's definitely a pattern here. Um, I made a table because these are both categorical variables between fasting blood sugar and sex. And the ratio is, it seems to like more the males have high blood sugar than the females. But the ratios aren't too different because there's fewer females in general. And in terms of cholesterol and sex, the males seem to have lower values of cholesterol on average, but not a huge difference. Um, And the people with higher fasting blood sugar tend to have maybe slightly higher fasting blood sugar. So, there's some patterns here, but nothing even remotely approaching collinearity because there's a lot of overlap in the distributions, or no pattern at all, and nothing that would be too highly correlated and that would mess up our models. So that's good to see. So again, in this example, there we knew this was going to be the case, but this is something you need to check. So that was it for exploratory analysis. And now we're going to move on to regression itself. So we're going to try to predict blood pressure in this toy example, which isn't much of an outcome variable, but it's a continuous variable that we can do linear regression on. Um, and just for this example. So we're going to use age, sex, cholesterol, and blood sugar to try to do that. So we're going to start with univariate regression. So just one at a time, can we predict blood pressure using age? Can we predict it using sex, etc.? And we'll just go through and see what sorts of models we get. Um, so this is how you create a linear regression model. As I said, you call this LM function on your R formula. And in this case, our formula is just that blood pressure is a function of age. So this is our formula. We tell it where the data is, and that's it. So that creates the model, it fits it, and then we can call the summary function to get the outputs and the confidence interval function to get the confidence intervals, and it's as easy as that. So let's do that.
Harry,
Yes.
just a question for you. Do you have any a priori reason to be assuming that there's a linear relationship between these factors and blood pressure? Or are you
No.
just hoping?
Just hoping.
Okay.
And sort of investigating whether there is, in a sense, with these models, because it'll tell you. And then, I'm also going to show you plots of these variables versus each other to see what that looks like. Um, but yeah, and I'll also show you you can do more complicated things. If your a priori assumption is that the relationship is quadratic or whatever you think it is, you can do that in a linear model. But for now, we're just starting with simple linear relationship,
Okay.
just to show you how to do this. So this is the outputs you get. It looks like a lot to read, but it tells you something about the residuals, which we'll get into in a second, and then the coefficients, so the intercept and the slope parameters. And that's really what I want to focus on. It tells you the error in these, the test statistic, and the p-value. It tells you something about the error, the R squared value, which I talked about yesterday, the adjusted R squared value, which I also talked about yesterday. So how much variance are we explaining? And that number adjusted for how many parameters we have. And then down here is the confidence intervals. So let's go through and interpret this output. We'll start with the slope parameter. So what this model is telling us is that for every 1 unit increase in age, and the units here are years, we're getting a 0.5 increase in millimeters of mercury in our response. And this is a highly, highly significant relationship. And our confidence interval is from the 95% confidence interval is from 0.38 to 0.62. So, in words, a 1 unit increase in age is associated with a 0.5 millimeter increase in resting blood pressure. So that's interesting. If we want to try to interpret this intercept, this is the value of the outcome when our predictors are equal to zero. But obviously, age being equal to zero doesn't really mean anything in this data set. So we have a problem here and we can't interpret this number. So that gets into something called centering, which I talked about yesterday, where you can subtract the mean of the value from itself and get a centered version of the variable. So we're going to do that here. We're going to make a new variable called C age, centered age, by subtracting the mean of age. So all this did is this was the regular distribution of age, and the distribution of C age is just shifted such that the mean is the new is zero now. And then if we make a new linear regression model between resting blood pressure and centered age, our values for the slope coefficient are exactly the same. The confidence intervals are the same. The p-value is the same. The slope estimate is the same. We're still saying for every 1 unit increase in age, there's a 0.5 increase in millimeters of mercury. But now this intercept is when the value of C age is equal to 0. So we can interpret that now. And we know that the mean in our data set of age is 53 and a half. So now we can say somebody with an age of 53 and a half would be expected to have a resting blood pressure of 132. So if you want to have interpretable intercepts in these models and you have continuous variables that don't have a meaningful 0, you need to center them so they do. And then finally, getting to Gabriel's question, let's actually look at this relationship. Like, did this make sense in retrospect? So this is a scatter plot of age and resting blood pressure. And this is a GG plot, scatter plot, so you can see it looks nice. And I've jittered the points because there was a lot of overlap, but people had the same blood pressure because of that weird rounding thing we saw. But this does look like something like a linear relationship visually. And in retrospect, it doesn't seem like any other type of shape would be better than a linear relationship here. It doesn't look super strong, but there's obviously some sort of relationship here. And you can actually add in what the line looks like if you want. And so this is something like what the regression model fit. But if you're assessing this manually, it's better to not put those lines because they can make you think things that aren't true because it'll find a pattern all over the place and you should do an eye test of whether this makes sense. But this does look like some sort of small but there linear relationship. So let's move on to sex. Before we told R that sex was a categorical variable. And I want to talk about how R handles categorical variables for a second. So let's run this box. This levels function tells us now what are the categories, basically. And the categories are female and male. And because of this ordering, which is just alphabetical here, female is going to be chosen as the reference category, it's called. And when R gets estimates for this variable, it's going to estimate the effect of being a male compared to that reference category. So compared to being a female. And if there was additional categories here, it would still be it would individually estimate effects of being in each category compared to being a female. So that's how R handles categories. And this is called dummy variables in a general sense. So we're going to make a new model with a new formula, which is just blood pressure is a function of sex. Again, we're telling it what the data is. So it's very easy to make these models. And then you just get our summary and our confidence intervals. So what the output's telling us now is that being a male, so being in the M sex category, compared to being a female, which is our reference category, is associated with a 0.4 millimeter increase in blood pressure, which is basically nothing. And this is a not a significant estimate because our p-value is high. And our 95 confidence interval for sex is encompassing 0. So it's well within the 95 confidence interval that there's no effect. And there might be this big range of effects. So R is telling us that it's not really finding any relationship here. And it's very uncertain what the relationship might be if it exists. And it's not significant and really small effect. The intercept value here, it's as always, it's the value of the outcome when all your predictors are equal to 0. And the predictor being equal to 0 in this case means being in the reference category. So not being in the male sex category, instead being in the female sex category. So we can interpret this estimate as if you're a female in this data set, your resting blood pressure is expected to be 132. So highly significant. And then we can again take a look and, visually there's no relationship here. So this output made sense. It didn't find anything. There doesn't seem to actually be anything. Now, this doesn't mean that in a multivariate analysis, we're not going to find anything. So that's why I don't necessarily advocate doing these univariate analysis. It's sort of just for the example. And so we can look one at a time at these variables, but this might still be an important variable in the multivariate analysis. But in a univariate way, it's not explaining anything. So that's that. Now let's do cholesterol. Same, same. We're going to be making a new formula. Resting blood pressure is a function of cholesterol. We're going to get the outputs. So, looking at the slope parameter, it's telling us that there's a 0.03 increase in millimeters of mercury per 1 unit increase in our predictor. And it's telling us that this is a significant relationship with a p-value of 0.009 and with a 95 confidence interval that doesn't overlap zero. And our intercept's not interpretable here, of course, because it's for a cholesterol value of zero. What is the value of blood pressure? That doesn't make any sense. So, does this mean anything? Is the question. And this is a good example of something that is telling you it's significant, but does it matter? Probably not. So, in order to prove that, because it's hard to think as a human on these weird fractional scales and to try to imagine what's going on. So let's change the units of our cholesterol value. And we'll also center it so the intercept's interpretable. So right now it's on, I think, milligrams per deciliter. It says it's millimeters per deciliter, which doesn't make any sense, but it must be this, which is the American value. Um, so right now it's telling us that a 1 milligram per deciliter increase in cholesterol is associated with a 0.03 increase in millimeters of mercury, which we're not really sure what's going on there. So let's change it to decigrams per deciliter, and then maybe we can get a better sense of what's going on. So we'll just divide the number by 100, essentially, and then we'll center it as well. And we'll run a new model with that modified cholesterol value. So we've now made cholesterol into this range where a 1 unit increase is a pretty big portion of the distribution. So we might be able to get a better sense of what's going on there. So it's now telling us that a 1 unit increase in this modified cholesterol value, and again, that would be a big chunk of your distribution, is associated with a 2.8 increase in millimeters of mercury. So a huge cholesterol increase for this, in real terms, pretty tiny increase in blood pressure. And it's statistically significant. But this is a good example of a relationship that is statistically significant, but probably not clinically significant. So, this is a good warning about the pitfalls of just looking at the p-value and then thinking it means all that much. The p-value is telling us this matters, but in real terms, it doesn't seem like it matters that much. And the intercept is now interpretable, of course, as we've centered it. So it's for a person of average cholesterol, what is their blood pressure? And then if we plot this relationship, if you just showed me this plot and said, is there a relationship? I'd probably say no, right? So beware of just looking at the p-values and trying to conclude anything. So R is fitting this line and telling you that this line is a significant increase statistically. But is the relationship really there? Probably not in any meaningful sense, because 3 millimeters of mercury for this huge jump in your cholesterol distribution, probably not important. Again, this doesn't mean it's not going to be important in the multivariate analysis, but in this univariate way, don't trust these numbers or don't think they matter, essentially. We'll finally do blood sugar, which is a categorical variable in this data set, so unhealthy versus healthy. So we can look at the levels again. So zeros and ones are the two levels. So zero is the reference category, which is healthy in this case, and one is the what we're going to estimate as a dummy variable, which is unhealthy. And what it's telling us is that having an unhealthy blood sugar is associated with a 3 millimeter mercury increase in blood pressure. And it's a significant relationship again, but obviously not a huge meaningful increase because 3 millimeters of mercury and then blood pressure is measured with air. So does this matter? Again, maybe not. And you can see visually that, yeah, maybe the people with high blood sugar have a slightly higher blood pressure, but there's a lot of overlap here. And this probably isn't a huge relationship, at least visually. So now that we've looked through one by one and, sort of more for example purposes than meaningful scientific purposes, let's make our actual model. So we're going to make a multivariate linear regression model by calling the LM function, modeling blood pressure as a function of age and sex and cholesterol and blood sugar altogether. So this is our new R formula. We're throwing in this linear regression model and we're telling it where that is. So again, incredibly easy to do this. You just add the terms together in your formula. And let's run this and see what we get. So this is the output. We have our intercept. We have our four slope parameters individually for the four variables. And the way you interpret these now is this 0.41 for age, for example. What it means is for a 1 unit increase in age, but holding these other three variables constant, what is the effect on blood pressure? So we're saying a 1 unit increase in age with equal values of sex, cholesterol, and blood sugar is associated with a 0.4 millimeter mercury increase in blood pressure. Highly significant. The estimate for sex is like a 1 unit increase, but non-significant. The estimate for cholesterol is a 2.3 millimeter increase, significant. And again, this is per 1 unit increase in our transformed cholesterol value. So a huge jump in the distribution being associated with a small increase, although it's significant, but clinically, probably not so much. And fasting blood sugar now having more of an effect, it seems like, and a more significant effect. So maybe there was some confounding going on, or adjustment for confounding. But this is maybe more of a real effect that a 5 millimeter mercury increase in blood pressure when you have unhealthy blood sugar. And then we have our confidence intervals down here. So basically, and then down here, I just put the confidence intervals for our univariate values just to show you that in terms of like clinical interpretation of what's going on here, it's actually quite similar to the story we would have told from just looking at the univariate relationships. So, age is probably the biggest driver here because a 1 unit increase is a 0.4 increase in blood pressure. So this is a pretty big effect here. And the other three variables, although these two have significant values, they're not huge effects. And sex doesn't seem to matter. So the story we tell ourselves looking at this is sort of the story I was just explaining before. Um, Another interesting thing to look at here is that our adjusted R-squared value is 0.08, which means in words, we are explaining about 8% of the variance in the outcome using our predictors, which is really not much. And then if we scroll back here, age alone was predicting around 7% of the variance. Sex predicted nothing at all. Actually, it hurt us to have sex as a predictor, basically. Um, less than 1% for cholesterol and less than 1% for blood sugar. So almost all of the predictive power here is coming from this age variable. Even though we're getting statistically significant results for cholesterol and blood sugar, we're mostly explaining blood pressure here in this multivariate model using age. The intercept now is holding all four of these variables at zero. What is the value? So this would be the blood pressure for somebody that has an average age, because we've entered it, is female, because that's the reference category for sex, has an average cholesterol, because we've centered it, and has a healthy blood sugar, because that's the reference category for blood sugar. So for people like that, we would expect them to have a blood pressure of 132 millimeters of mercury. Right. So most of the explanatory power in this model is coming from age. So now let's take a look at the residuals. So the residuals are the difference, as I said yesterday, between what we're predicting and their actual values, and what we're predicting using our fitted model. And by looking at the residuals, you can tell a lot about your assumptions of the model and whether they're met or not. So we'll make a complete version of it. Oh, there's one more thing I wanted to mention, which is 172 of the observations were deleted due to missing this. So we told R that 172 people had missing values of cholesterol. And R doesn't then it can't do anything with these people because it needs the value to estimate the effect. So it just deletes them, which often is going to be a problem for you. So, I didn't get into it yesterday. I'm not going to get into it today too much because it's very complicated. But what you can do is impute missing values and then put them in your models. And if you're doing that, you should do something called multiple imputation. Some people do something called mean imputation, where they just replace the value with the mean value in the data set, or like median imputation. Don't do that. That is very bad practice. You need to do something called multiple imputation, and you can look up what that is and how to do it. But I'll just say, R is deleting these people because we don't have the data on them. And that's the only way forward unless you're doing something to try to replace them in some good way. Um, so since we deleted those people, we have to delete them from our residuals as well. And then you just call this residuals object from our fitted model, which was just what we created for our multivariate model. And then we're just going to plot those residuals and see what they look like. So these are the errors in our estimates of blood pressure. So we're predicting blood pressure with a lot of error here, obviously. But in terms of our assumptions, we don't really care that this error is big. What we care about is that it's normal. And this actually does look pretty normal. So that was one of our key assumptions, that the errors are normal, and this looks normal. And you can call this QQ norm function, which is the quantiles that would be theoretically generated by a normal distribution compared to your actual sample quantiles and residuals. And this looks pretty much like a straight line. It's never going to be perfect in actual data, but this looks more or less like a normal distribution. So that's how you check whether your errors are normal, and these are, which is great. Um, we can also look at the residuals versus each of the predictor parameters. So just plotting them against each other. And what we want to see here is that there was a couple of our assumptions from yesterday, which one was that the variance is constant across the range of your predictor parameter, so that you don't see some weird, like it's small error at low ages and high error at high ages. Um, so we're not seeing that here. This looks pretty random, which is exactly what you want to see. Um, no particular pattern and you also don't want to see anything like a weird quadratic relationship here, because that would indicate that the actual relationship wasn't linear between age and blood pressure, which again here, there's nothing like that. This just looks random. There's no particular pattern for the residuals versus sex, or the residuals versus cholesterol, or the residuals versus fasting blood sugar. So we've checked those two assumptions now, and so those both are met. Our variance looks pretty constant across the range of our predictors, and there's no particular pattern, so it looks pretty linear. And as we checked before, the residuals look pretty normal. So this is how you check your assumptions for linear regression, and you should be doing this. A lot of people don't, but it'll tell you whether you can rely on the effect estimates that you were getting, because if those assumptions are violated, then you can't rely on your effect estimates. Um, there's something I didn't talk about yesterday, but you can check how influential individual observations are. And this is important because you might have like outliers that are really driving a lot of the apparent effect, and you don't want that to be happening. Um, there's something called Cook's distance, which I won't get into what it actually is, but it's essentially an estimate of how much your effect estimates would change if you deleted observations. Um, and a large value indicates a large influence on the regression function, which you don't want to see. And as a simple rule of thumb, you don't want this value to be more than 1. So we can plot this, and our values are very small, nowhere near 1. So, there's some observations that had much bigger effects than a lot of others on our regression function, but overall, the absolute values are pretty small, and we're happy to see this. Another thing you can do is in R, just call this plot function on your regression model, and it'll generate these plots automatically. Up here, I did it all manually to show you what's actually going on, but this will just generate them automatically. So this is sort of interesting. um, this wasn't as obvious from the above graphs, but this is the full fitted value versus the residuals. And you see these weird patterns, right? And so in the error, we're getting these like bands of error. And we saw that before. We know why this is the case because we did our exploratory analysis. It's because blood pressure was measured with this weird error. So this is just manifesting these rounding error in our outcome variable is manifesting as clustered error in our predictions, which makes sense. So, we're not happy about this, and maybe if you wanted to do a more complete analysis and this was an actual research question, you would try to fix this error and spread it out to get rid of this pattern. But that's what's going on. This is just the QQ plot again, which looks normal. This is just a scaled version of that first plot, which again we're seeing these weird bands of error. And this is a Cook's distance plot essentially. Well, it's something slightly different. It's leverage, but um, again, there's nothing surpassing Cook's distance when you standardize it. So same plots, just a little bit more complicated. If you want to look at that, um, but again, nothing too extreme, and we're happy with these assumption checks, and we can rely on our estimates from our linear regression model. Um, I also want to show you what would happen if we used model selection. So I'm going to load this library, which is in Google Colab already. And we're going to use step AIC. So I talked a little bit about AIC yesterday. I think it does output it automatically. No, it actually doesn't. Anyway, AIC is an estimate of how good your model's fitting, essentially, based on likelihood. And the step function, and it'll be obvious when you see the trace, but it goes through all your variables and it says if we dropped these variables or if we added new ones in, would our predictions improve or get worse? And so it generates automatically for you essentially the best possible combination of your variables for your question. And again, this is a dangerous thing to be doing, but I just want to show you how to do it anyway, if you're interested. It's safer to do in this sort of situation where we have way more data than we need, and we can get a little flexible with how we're modeling because we have degrees of freedom to burn on this kind of thing. So we start with our full model here. So this is just the full model we fit. So at the start, our AIC was this number, and the absolute value of AIC doesn't really matter. What matters is the difference between models. Um, and then I turned trace on so you could see what's happening here. So we started with this full model, and then we asked ourselves if we delete any of these four variables, what's going to happen to our AIC? And you want AIC to be a small number. And R found that if we delete the sex variable, our AIC goes down. So this number is lower than this number. So it deletes sex. And then it asks the same question. If we delete these four variables, or now we have sex that's not in it, or if we add it back in, and obviously we're not going to delete it, then add it straight back in, but it goes backwards and forwards over and over again and picks the best addition or deletion to get to the optimum. Would either adding sex or deleting any of these three now from this smaller model improve our AIC? And in this case, not doing anything gives you the best AIC. So this was a pretty simple one-step example of this, but R decided that deleting sex helps, and then from the smaller function, keeping it as is the best. So it's recommending we go with this model. So this model, out of our four predictor variables, gives us the best fit. So again, be very careful when you're doing this. And if you thought sex was going to influence blood pressure a priori, don't delete it just because this happened. Keep it in. But if you have a more complicated situation and you know what you're doing, then this can be an okay thing to do to sort of find the best model. Next thing I want to show you is effect modification. So we're going to add an interaction effect here between age and blood sugar. And I played around a bit here to get a significant effect, which is, of course, bad practice. Um, and importantly, I chose one continuous predictor and one categorical predictor because that'll let us pretty easily interpret what's going on. So adding an interaction effect, as I explained yesterday, is just saying that there's some effect on blood pressure of age, for example, when you have high blood sugar versus when you don't. So there's a differential effect. The effect is modified in different categories of people. And you can just add a multiplication of those two variables to estimate this. And this is actually just a straight up multiplication. So how we interpret this now is you have to interpret the effects with respect to each other. So our age effect estimate now is we're saying that this is the slope. So we're saying that for a 1 unit increase in age, we're getting a 0.4 increase in millimeters of mercury. But you have to interpret that with respect to the interaction term, which is now in there. And what this interaction term is telling us is that, so if our fasting blood sugar is 0, so if we're in our reference category, then this interaction, this multiplication is going to be 0, and this interaction term will not apply. So this interaction term only applies to people that have a fasting blood sugar of 1. So what we're saying is in people that have unhealthy fasting blood sugar, every unit increase in age is associated with an additional 0.4 increase in millimeters of mercury. And R is estimating this is a significant effect. So this is a large interaction effect, actually. So in people that don't have high blood sugar, we're seeing a 0.4 increase in millimeters of mercury. And the people that do, we're seeing a 0.76 increase in millimeters of mercury per year, which is a huge effect, actually. So obviously, talking this through it's complicated, right? And this is a simple example of an interaction effect. So be careful when you're doing these interpretations. Um, and I'll just say it again because of how complicated this is. So if we're saying somebody has a low blood sugar, then this interaction term does not apply. And we're saying that they get a 0.4 increase in millimeters of mercury per year of age. If they do have a high blood sugar, then the interaction term does apply. And they get an additional 0.4 increase in millimeters of mercury per year of age. So it seems like the effect of blood sugar on blood pressure might depend on age, or you could say the opposite statement, that the effect of age on blood pressure might depend on blood sugar because they're interacting with each other. And there's more of an effect in older people, or more of an effect in people that have high blood sugar. So, maybe if we're trying to put this in some sort of clinical interpretation, we can say that maybe metabolic syndrome has more time to affect the body in older individuals. And if you want to see what this looks like graphically, the people that have high blood sugar have a higher slope of the interaction of the effect of age on blood pressure than the people that have a low blood sugar. So this is what we're talking about. This is what went on. And, this is sort of a cool result that there's an, more pronounced effect of blood sugar on resting blood pressure or vice versa with high of the other. So that's interaction effects. Just a quick word on polynomials. We won't go too much into this, but as I said yesterday, this is linear regression in the sense that it's linear between your x's that you put in here and your outcome, but you can do things like square your variables, and then it becomes linear in a quadratic sense. And we saw earlier that we're not really expecting any quadratic relationship, and indeed there's nothing found here for age. But you can put quadratic terms in, or cubics, or whatever you want. And you can actually create quite complex relationships between your variables and your outcomes if you want to. You can also do things like splines, which I'll get into, and which gets extremely complicated, but this is just a basis spline of third degree for age. And so it's linear, so it's simple, but it can get very complicated if you want it to. You just need enough data to fit that kind of model. Right. So we can also generate predictions. So we can use our model to make predictions, essentially. So if we want to ask, if we had a 70-year-old man with a cholesterol of 200 and a healthy blood sugar level, so we'll create that example person. We'll say that we have to modify these numbers to get back to the the type of variable we have, which is centered age and centered cholesterol divided by 100 and centered. Um, and sex is the category, so we have to tell it it's a factor. And blood sugar is the category, so we tell it it's a factor. But we create this example person, and then we just create a prediction for this person. So you can do this with any numbers you want, and you can ask this question: well, what are we predicting? And in this case, we're predicting that this type of person would have blood pressure of 144 millimeters of mercury, and you have the uncertainty in these predictions as well. And then you can ask questions like, what if we had the same person, but instead of having healthy blood sugar, he had unhealthy blood sugar? So we'll just replace his blood sugar with unhealthy and we'll run that. And now it's 149 millimeters of mercury. And the reason this went up by 5 is because our estimate for the effective blood sugar was 5, right? So in the simple example, that's all that went on. Um, so you can get predictions for any type of person you want using these models. And I'll just say that their parameters should be in the range of your data, or else you're extrapolating, and that can get weird. So that's how you do predictions. So I'm going to move on to logistic regression, but are there any questions before I do?
Yeah, can you hear me?
Yeah.
Yeah, I have a question about the interaction terms. It seems like your decision of uh, making what that the fifth parameter is, the variable is the interaction term was quite based on some a priori knowledge. So when you're in the process of coming up with what your interaction term are going to be or what you want to explore with, what are your sort of basic rule of thumbs in coming up with them? And would it be for exploratory purposes, or you just want to see what they're going to be like, or what's the end goal when you're exploring the interaction
Yeah.
terms?
So this should be a priori. Like it should be that you think ahead of time there's going to be some interaction between these variables. I actually didn't do this a priori. I played around until I found something nice that I could show you where there is an interaction. Um, so yeah, only do this if you think a priori that there's going to be. And we can see we have this huge data set, and it seems to be a pretty big effect, but still
Mm,
R is barely calling this significant. So it's very hard to estimate interaction effects.
right.
Uh, you need a lot of sample to do that accurately. And that ties into what I was saying about machine learning, where you need huge samples to accurately generate predictions in machine learning, because there's interaction sort of explicitly, implicitly. Um, but but yeah, you can find some very cool things like this. It's just you should have some idea ahead of time that there's going to be a difference in the effect of age on blood pressure in people that have high blood sugar.
And would
Uh,
you say these should be reported, the interaction effect, if you were to actually find something significant, would you write that in your paper?
Absolutely.
Or yeah,
Yeah, absolutely. Because this is a big change in the interpretation of what's going on here. And we're really saying that people that have high blood sugar have a much more pronounced effect of age, or vice versa.
and sort of what should you avoid doing in terms of playing
You should
around?
avoid you should avoid doing what I did, which is just putting every possible interaction in and seeing what the most interesting one is, and then pretending like that matters. Um, this should be specified ahead of time if you want to rely on this.
Okay, thanks.
Um, okay, so I only have half an hour left, so it's been going slower than I expected. I'm sorry about that. But I'm going to show you how to do logistic regression next. Um, and I'll really just focus on the interpretation here, and might not have a time to get to goodness of fit as much. Although I imagine your machine learning classes will be covering that as well. So we're going to do our actual outcome variable now, which is heart disease, which is the more interesting variable in the data set. And we're going to start with univariate regressions. So we'll start with heart disease as a function of age. We're using the GLM function to make a uh, logistic regression by telling it that the length should be by a binomial distribution. And then, as with linear regression, we can just call our summary function to get out the effect estimates. Although, as I explained yesterday in some detail, just looking at these effect estimates doesn't really tell you anything, because this is on some weird log odds scale.
So what we need to do is exponentiate our coefficients to get something interpretable. So this is the exponentiated value for age for the slope parameter. So it's the exponential of this. And this is the interpretable number. So when you exponentiate age, the slope parameter, you get 1.07. And what this tells you is that for a 1 unit increase in age, we have 1.07 times the odds. So this is an odds ratio. We have 1.07 times the odds of having heart disease for a 1 unit increase in age. And you can exponentiate your confidence intervals and get your 95% confidence intervals. You just exponentiate it. Here actually. And 1.07 times might not sound like a huge number, but this is actually a really huge effect because it's 1.07 times per year. So if you have a 2 year increase in age, it's 1.07 times 1.07. So this is compounding over the years. So if you have a 10 unit increase in age, it's this number to the power of 10, which is 1.9. So somebody 10 years older than somebody else has 1.9 times the odds of having heart disease. So this is a huge effect. And we can interpret our intercept as well. You have to do this weird transformation to get back to the probability. But we're saying that somebody of average age in this data set has a 56% chance of having heart disease. And seems high, but it's just because this data set has a lot of people with heart disease in it. So this is a highly significant estimate, highly clinically significant as well, and with a really small p-value. And you can see this graphically, where the people that have heart disease are much older. And this is just a plot showing the same thing, but the people that have heart disease tend to be much older. And I put some alpha on these plot numbers here, where you can see that the distribution of people with heart disease is quite a bit older than the people without. So we'll do a univariate analysis for sex just to really drive home this point about interpretation. Our actual sex parameter doesn't really tell us much. You need to exponentiate it to get to something interpretable, which is 4.9 exponentiated. And this is another huge effect. So men compared to women have 4.9 times the odds of having heart disease in this sample. And this is highly significant. Our confidence intervals, we can exponentiate to get them. And then our intercept now is for the value of sex being 0. And again, females are a reference category here. We're estimating the effects of being male compared to being female. So females in this data set have only a 26% chance of having heart disease, even though most of our data set has heart disease. So it's really the males that have heart disease in this data set, which fits with real life. We can look at this graphically where the males there's more males than the people that have heart disease compared to not, a bigger ratio. And since both of our categories here, a predictor and our outcome are both categorical in this case, we can actually explicitly show you what's going on here. So in males, 458 of them had heart disease and 267 didn't. In females, 50 had heart disease and 143 didn't. So you can obviously see the huge difference there. And you can calculate the probability of having heart disease in women, which is 26%, which is our intercept. You can calculate the probability in men. You can calculate the odds in men and women, which is just the odds is this number over this number. So the odds of having heart disease in men is 458 over 256, and the opposite in women. And this 4.9 that we got was an odds ratio, which is simply the ratio of the odds in men to the odds in women. So you can quite easily, this is an intuitive way to tell what's going on here with these odds ratios. And this number is 4.9. So this model just did that for us. It told us that being a man compared to women is a 4.9 times the odds of having heart disease, which we could have done manually just by looking at this table and calculating the odds of men and the odds of women and seeing what the odds ratio was. So in this case, in logistic regression, where you have one variable and your outcomes binary and your variables binary, you can just make this 2x2 table and do it yourself. So I think this is a good way to understand what's going on here as it gets more complicated. We'll just quickly go through cholesterol because I kind of want to get to some of the more interesting stuff. So we're saying that a 1 unit increase in cholesterol is 1.4 times the odds of having heart disease, which seems like a bigger effect than it was for blood pressure. And this is a significant value. And we can look at this graphically where the people with, that have heart disease have higher cholesterol, although it's not a huge effect. For blood sugar, this is categorical again, but we're saying that people with unhealthy blood sugar have 4 times the odds of having heart disease. So this is another big effect. And we can look at this graphically where it's another big effect in a tabular format. And again, we could do this manual calculation of the odds in unhealthy people with unhealthy blood sugar versus not, and then do this manually, and you would get 4.18 if you did this manually. And then if we add all these together in multivariate regression, so this is interesting. The effect for fasting blood sugar, which was something like 4 times the odds in the univariate analysis, is no longer significant. And probably this relates to relationships between fasting blood sugar and sex, for example, which is now an even bigger effect. So this maybe is some sort of confounding of sex and blood sugar, where sex, including it in this multivariate analysis, has removed the effect of blood sugar, which is no longer significant, and now overlaps 1, which 1 meaning that there's 1 times the odds, which is no effect. And then, sex has this huge effect, age has this huge effect, even though the numbers are small. You have to remember this is for 1 year and it's compounding. And cholesterol has a pretty big effect too, although we're not seeing much of an effect for blood sugar in this multivariate analysis. And you can do step AIC again, and in this case, it's going to tell you that all the variables matter. So even though blood sugar was not significant, we keep it in according to this AIC measure. As with linear regression, you can do predictions. You can generate these example people by just inputting their made up variables, and you can ask the model to predict for you. And you can tell it, give me a response. So give me it on the scale of the response variable, which is a 0 or a 1 for having heart disease. And so if we have a 70-year-old man with normal-ish cholesterol and normal blood sugar, we're saying a 91% chance of having heart disease. So being an old man in the status set gives you a very, very high chance of having heart disease. And if we just switch the 7-year-old person to a woman, it's down to 67%. So you can see this extreme effect of being a man in these predictions. Okay, so finally getting into goodness of fit, which is sort of the more interesting part. So this is a whole bunch of code which is doing manually what can be done very easily using the PROC package by just calling AUC. But this code is doing that. I'm estimating the sensitivity and specificity at a certain threshold, and then I'm iterating through all thresholds between 0 and 1. And I'm estimating the sensitivity and specificity. And this is what I explained yesterday. So this is just doing it manually. So don't worry about what's actually going on in the code. But you can see the sensitivity and specificity at 0.5 threshold, at 0.4 threshold, at 0.3 threshold. So we're saying if the predicted value is more than 0.5 chance of having heart disease, we're going to call that a heart disease case. And 0.4 as a threshold, 0.3, and you can see the different specificities and sensitivities. And then as you range through every possible value and plot them, this is the AUC. And then this code down here is just manually calculating the area under the curve using the trapezoid method, which is a ridiculous way to do it. But so just use that package if you're doing this yourself. But we're getting an AUC of 0.71. So that's our AUC value for the status set, which is fine. 0.5 is chance, 1 would be perfect. This is our estimated AUC value. And this is our receiver operating curve done manually. But again, use the PROC package if you're doing this yourself. But we might be overfitting, right? As I explained yesterday. So now we're going to load Frank Carell's package, which we installed earlier. And if you missed the earlier part of this talk, you won't be able to run the cell, but you can try to install it right at the start quickly and then come back and you can run this stuff. So Frank Carell's package has this very convenient way to do validation. Either bootstrap or cross validation. It's very simple. So we have to create a new logistic regression model in Frank Harrell's package, but it's the same form. We're just using the LRM function instead of the GLM function, but it's logistic regression model. Um, and then we run this validate function, which does internal validation for us. And I'm doing bootstrap validation here with 500 bootstraps. Although you can play around with this, and I'll show you cross validation in a second. So as I explained yesterday, this is creating bootstrap samples. It's fitting regression models in that bootstrap sample, and it's fitting regression models in the original data. So this 500 bootstraps that just fit 1,000 different models. And we're getting the average results here. So Frank Harrell hates AUC, so he doesn't provide it because he doesn't want people using it. But we can convert this DXY value to AUC just for our purposes. And there's a simple relationship, C or AUC. And DXY has this relationship. So you just divide DXY by 2 and add a half. So our original value was 0.5022, which converts to a AUC of 0.711, which is what we calculated manually. The corrected AUC, and this is the value after bootstrap validation, is 0.4938. So we can convert that to AUC and we get 0.746. So this isn't a huge difference, actually. So we weren't overfitting that much, which is great. And this has to do with the fact that we had a nice big sample size, I think. And so we were pretty reliably fitting this model and not overfitting too much, which is nice. You can also plot calibration curves in Frank Harrell's package. So this is just a plot of what we're predicting for heart disease versus the actual probabilities of heart disease binned. And we're seeing this really nice relationship where we're pretty accurately predicting heart disease with, some degree of error. And he plots the apparent performance here and the bias corrected performance, which aren't very different in this case. So we're not overfitting very much. And then this is if you want to do cross validation, folds. So it's the same function, but we just tell it to do cross validation with 5 folds in this case. And we get our cross-validated estimated performance very quick. And I just want to show you that as you run this over and over again, your value changes quite a bit. So this is the problem with cross-validation. It depends on your folds. So if you're doing cross-validation, run it over and over again and take the average, is what I'll say, so that it doesn't depend on much on your fold. Or just do bootstrap validation, which is much more stable because there's way more models fit. Okay, I actually got through that faster than I thought. So we have time to just take this one last interesting thing, which is showing you more of a use case for stepwise variable selection, although it's very sketchy. So I want to show you, taking a maximalist approach, how good can we make these predictions? So before we had, like in this model, we had a prediction accuracy AUC of 0.75. How good can we make this if we use everything and we, greedily use variable selection and we see how good we can get? So we're just going to reload the data frame. We're going to correct these errors in cholesterol and resting blood pressure that we found. There doesn't seem to be any errors in the rest of the data. There might be some errors in this old peak value, but these might actually be 0. I don't know enough about EKG to tell you whether 0 is a real value or not for this data frame, which is the danger of using 0 as your missing value number. Never do that. But let's just pretend that it's the actual value here and that, there's no missing values and that everything's there. We'll take a look at sample size quickly. So we have 356 events in this full data frame. And if we're using our 20 predictor parameter rule of thumb, that lets us use 18-ish parameters. And we have 11 possible predictors, although some of them have multiple parameters. But we have 15 parameters in these 11 predictors. So we can use all of them, which is good. So this isn't too crazy what we're doing here in terms of accuracy and stability. So using Frank Harrell's data, we're going to use this as a function of dot, just uses everything in the data frame as predictors. And we're going to create these predictions. So Frank Harrell actually does the exponentiation for you, which is nice. So the effective age here, exponentiated, the odds ratio is 1.5 per year. which again this is an even crazier effect. And then we have our estimates for cholesterol and blood sugar and you know, for chest pain, we now have multiple categories, and our reference category is being asymptomatic. So we have estimates for being of this pain type or this pain type or this pain type separately. So this is Frank Harrell's version of what we were doing before, which is, in a lot of ways easier to read, but he makes it hard for you to do things because he doesn't think you should be doing them, which can be a pain. Um, and then we're going to use Frank Harrell's stepwise variable selection algorithm, which this is like stepwise AIC, and I'm telling it to use AIC actually, so it's equivalent. Um, and we're going to, using this full model, using all these possible parameters, we're going to do stepwise variable selection, and we're going to see which ones to keep. So this now had a more interesting result. I didn't put the full trace here, but it deleted resting EKG, max heart rate, blood sugar, cholesterol, and blood pressure. It says we don't need these variables. Let's just keep these ones. And then we're going to create a new model using only these variables that told us to keep, because that gives us the best AIC. And we're going to run internal validation using 500 bootstrapped samples. And now our DXY value is 0.84, which is an AUC of 0.92. And our R squared is 0.65. So we're now explaining 65% of the variance. And we're having, almost perfect predictions, even after internal validation. So, wow, this seems really good. And it's still nicely calibrated. But here's the warning before I finish and take any questions in the last 5 minutes, is that, like this is sort of a blind way to just maximize prediction. We're going to get the best predictions we can, and we're not going to think too much about what's in the data. And this is what I really want to warn you about, not taking this approach I just took, blindly doing things. Because, you might report this in some paper and say, look how good our predictions are. We're almost perfectly predicting heart disease using this data. But is it fair? No, it's not fair, because we're using things like chest pain, angina, EKG measurements. And if you have these things in your data sets, then you know if they have heart disease or not, right? You don't need to be making this prediction. So just think a little bit about what your variables are and what they mean and whether they would be clinically useful. Because this model, even though after internal validation we're getting this very nice performance, is not a useful model. Because if we have this data, we already know whether they have heart disease. So think about the context of your data. Don't just blindly apply these models and then think it matters what your output is, or especially don't concentrate on just, oh, our AOC is so good, this must be a great model. Think about the usefulness of what's actually going on. Great. So made it in time. I know that was a huge amount to go over, but you have the code. You can go through yourself. And if you want to do this yourself, there's a lot of resources out there. I really recommend Frank Harrell's book to explain sort of the principles underlying this stuff and how to be careful with it. But are there any questions? We have 7-ish minutes, and I can stay later if you guys want for questions.
I'll ask a question. Thanks, Harry.
Yeah.
So this maximalist prediction last section is actually one of the first times I heard this name. Do people actually report this in their papers and call it maximalist prediction, or
No.
they just kind of do it, or you came up with this term?
I'm just saying that this is the maximalist approach,
Oh, okay.
like maximizing AUC.
Right. It seems like the package sort of still buried some steps inside. Like I maybe it was fast, but I didn't quite catch how it selected the best variables to do this maximal.
So I started with every possible variable
right.
in this model, and then I told it to do as we did above, and I showed you the trace above, to go one at a time and figure out which variable should be deleted based on AIC. So it's minimizing AIC. So it's what set of variables out of all the possible combinations give you the best AIC.
Right.
And this isn't an exhaustive search. There's ways to do exhaustive searches, but it tends to converge to the exhaustive search result. So it chose the variables that predict heart disease with the best AIC.
Right. And then your next line did the actual best predictors refitted it, right?
I refitted it using these ones it told me to keep,
Yeah.
and then I internally validated that fit,
Yeah.
which isn't overfitting that much actually. I mean, it is a little bit, but not too much. And our validated AIC is, well, it's actually a tiny bit different here because it's a different run and it's random, but is high.
Yeah. And previously in your bootstrapping versus cross-validation approaches in R, um, it's true that every time you rerun the cross-validation, the results sort of change because of the fold configuration changes. But I wonder if you rerun the bootstrap 500 times every time you click and run, would that change the numbers too? It probably
Yeah,
would a
I
little
mean
bit as well. Yeah.
it does change a little bit, but it's much more stable
Right.
than the cross validation. And if you want it even more stable, you can crank up this 500 number.
Yeah. Yeah.
Um, but yeah, it's almost the same number compared to cross validation, which is not.
Great. Does anybody else have any questions? If not, thank you, Harry, again for your session yesterday and today. The next one will be, well, go more full steam ahead into actual classical machine learning. And these two sessions give really good statistical rigor and warnings by Harry. And next session we'll have Farhood to code more in Python actually later on, which we'll see you guys on Thursday and then Friday.
So everyone, and feel free to email me or if you have any questions or yeah.
Great. Thank you.